Hey, physics babies. Welcome to another day of online learning. Today, we are going to be talking about electromagnetic waves. We're almost done with this unit, so pretty exciting. Let's get started. I actually have something I want to show you as for you to kind of be thinking about throughout the lesson. So the last question on your assessment for the day, I just kind of wanted to give you an overview because this does look a little different than the questions I normally ask. So you are going to organize these electromagnetic waves from lowest energy to highest energy. So as an example, if I think gamma rays are the lowest energy, I'm going to click that. Then as we move down to the next row, tell me which of these waves that are left do you think has the next level of energy? So I'm going to say infrared. And then the next one is radio, right? And you fill it in, so each column will be checked one time, and each row will be checked one time. I hope that makes sense. If you have any questions or concerns, please feel free to reach out to me. Email, comments, phone, message, whatever, all right? And I will do my best to help you out. All right, though, moving on to our actual lesson. So this is Unit 6, Lesson 4, Electromagnetic Waves. Here we go. So the objective, by the end of the day today, you'll be able to explain the relationship between frequency and energy of electromagnetic waves, and you'll also be able to calculate the frequency and wavelength of an electromagnetic wave. Make sure you've got your notebooks out, and here we go. So electromagnetic waves. Electromagnetic waves are transverse waves that can transfer energy through both matter and empty space. This is a little bit different than our sound waves that we were talking about last class. Our sound waves, or mechanical waves, needed to have matter to travel through. These EM waves, as they're frequently called for electromagnetic, are transverse, so they do the nice sine curves that we love, and they can travel through matter, but they can also travel through empty space or a vacuum. And that, my lovelies, is why we can see light from stars that are out in space. That light is able to travel through the vacuum of space to reach us. So here is our electromagnetic spectrum. Please make sure you kind of jot this down, pause me, do it to it. So as we move from the right to the left, we are increasing in energy. So that means as we move left to right, we are decreasing in energy along this spectrum. As we move from left to right, we are increasing wavelength. So the less energy, the larger the wavelength. Less energy, larger wavelength. So we've got a whole bunch of waves. Some of these you might be familiar with, some of them maybe not. All the way over here at 0.0001 nanometers, we have gamma rays. In between 0.01 nanometers and 10 nanometers, we find X-rays. So that includes the medical X-rays that we use, and for like dental X-rays, broken bones, et cetera, et cetera. At 10 nanometers to about, it's a little like 350-ish, we have ultraviolet. And ultraviolet is actually what we get from the sun. We get some visible light rays from the sun, but we also get ultraviolet, and that's what will give you a sunburn. Now we've got our visible light, and that's between 350 nanometers and about 750, 770, 800-ish nanometers. Then we move into infrared, which is, from the edge of our red wavelength to, almost 1 centimeter. Then we start getting radio waves, and that includes radar, TV, FM radio, and AM radio. That's why we have 2 different radios, right? They operate at 2 different sizes of wavelength, and that's why you're able to kind of get access to both in your car. Please, again, copy this diagram down and make sure to make a note. 1 nanometer is equal to 10 to the negative 9 meters. These are really, really, really small. All right, When you're ready, let's keep going. So, our relationship of light. Frequency and energy have a direct relationship. A direct relationship means that as one goes up, so does the other. All right? So, if we increase the frequency of our wave, we also increase its energy. On the other hand, frequency and wavelength have an inverse relationship. So that means if we increase the frequency of our wave, we decrease its wavelength. Please make sure you copy down both of these graphs into your notes and explain their relationship. Super important that you know this. Okay. So again, looking at our electromagnetic spectrum, if we increase the energy, what else increased? The frequency. If we increase the frequency, what happens? Our wavelength will decrease. So higher frequency waves mean they have more energy. All right. Okay, moving into our visible light spectrum. This visible light is a narrow band of wavelengths that our human eyes can actually see. Now, visible light is a little specific as you start thinking about different species, right? But for us as humans, our visible light we see from red to violet, okay? Every color of light that we see operates at a different wavelength and frequency, and that's what gives us those different colors. So red light is the longest wavelength and it has the lowest frequency, whereas blue and violet have the shortest wavelengths and the highest frequency. Thinking back to our relationships, if we have a short wavelength and a high frequency, what does that tell you about the energy of that wave? Take a second, think about it. It means that our blue light will have our violet light will have the most energy. Okay. So take a moment, please, and jot down this table that we see that's got our colors of visible light. It specifically tells us the wavelengths that each of these colors operate in. And this will be important because it's a very fair question for me to ask you to find a wavelength of light and then tell me what color that light would be, okay? Something else that might help you as you are writing these down, I would maybe include the value of these in meters. So this is 6.25 times 10 to the -7 meters. Okay, you could take each of these numbers, add a little decimal, and put times 10 to the -7 meters to help you with any calculations. Remember, we use meters, we use kilograms, and we use liters as our standard units of measure. All right. These values are just so small and they're so commonly seen that sometimes it seems a little silly to write times 10 to the -7 meters when we're talking about red light. But your calculations will say times 10 to the -7 on your calculator. So make sure you understand that conversion. All right, speed of light. We call it c. It is a constant. Lowercase c, it is always representing the speed of light. Our units are meters per second, as always, and light travels at about 3.0 times 10 to the 8 meters per second in a vacuum. So this is for light, any electromagnetic rays that we get here. We can calculate their wavelength or frequency using that same formula that we learned in our last lesson before that. Remember, it was written out V equals lambda times F, where lambda was our wavelength, F was our frequency, and V was the velocity. In this equation, specifically for light, we know the velocity. We know the velocity of light is always 3.0 times 10 to the 8 meters per second. So instead of saying V, we call it C, constant speed of light. Please make sure you've got this written down. All right, next question. In the visible light spectrum, which color has the most energy and which color has the least energy? Please jot down your answers in your notebook, and then when you are ready, pause the video, jot it down, and when you're ready, resume. So, violet and indigo waves have the highest energy because they have the highest frequency. They've got the smallest wavelength, small wavelength, big frequency, big energy. Red light, on the other hand, has our lowest energy, all right? It's got the longest wavelength, so it has the lowest frequency, which means it has the lowest energy. Large, low, low. That might help. Maybe jot that down. All right, moving on. My next question, which color of the visible spectrum of electromagnetic waves travels the fastest in a vacuum? Pick your answer, and when you are, pause it, pick your answer, and when you're ready, let's move on. So, what did you pick? Hopefully you picked D, none of the above, because we just got done saying that light is a constant. It all travels at 3.0 times 10 to the 8 meters per second. It doesn't matter what color it is. It's got that same velocity. So all light travels at 3.0 times 10 to the 8 meters per second in a vacuum. The light changes speed and bends as it enters other materials. So the problems that I ask you about will be in a vacuum. But it's important that you know and that you write down that our light will change speed and bend as it enters materials. So in less dense materials, our light will speed up because the frequency will go up. In more dense materials, the light will slow down because the frequency will go down. Remember, our frequency is kind of like how many wavelengths we get per second. So if we have less stuff, less density, more of that light can get through. If we have more dense material, so there's more stuff for the light to pass through, it's going to slow the light down because it can't move as freely through the material. I will see, I'm trying to show you guys a demo. If I'm able to get it to work, I will put it in the next video. You know the, like you've got a prism and we see light entering it and we can see how it separates into the colors. Think Pink Floyd, right? The prism. So I'd like to be able to show you that. I haven't figured out how to get it to work so that you guys would actually be able to see it on camera. Keep your fingers crossed. But that prism is a material that causes all of the visible light that we have, right? White light is composed of all colors of light, right? So we've got red through violet in white light. That prism causes the light to slow down and separate into its different distinct colors. It's really cool. So I'd love to be able to show you. Wish me luck. But if I can't make it work, you should still go and try and find a demo. Just go to YouTube and look up light separation physics demo. I'm sure you'll be able to find something cool, okay? If you find any good ones, please link them in the comments to this video. All right, next question. Why can people go into a tanning bed to absorb ultraviolet light wearing bathing suits and be relatively safe, but medical patients getting x-rays need a protective gear to cover their chest when they get an x-ray? So if you've ever gotten an x-ray, like especially for at the dentist, they put a lead apron on you while you are getting x-rayed. If you get an x-ray for a broken arm, right, they'll make you wear a lead apron to cover as much of your body as possible. Why is that? Take a second, pause me, write down your answers. All right, so here we go. X-rays have a higher frequency than UV light, right? If they've got a higher frequency, they've got more energy. That energy can actually harm the DNA within our cells. It can start causing mutations, it can cause damage, and we don't want that. So we wear protective gear to prevent against X-rays. Gamma rays are even more damaging to humans. And so like gamma rays are when we have nuclear stuff going on, right? Fusion, fission, those typically release gamma rays. They're very, very high energy. And, you know, we've been able to contain them in some ways, right? Minus, you know, Chernobyl, to actually like contain and then harvest that energy. But it is a very unique, special, and dangerous process that we need to make sure we kind of take proper precautions on. All right, almost done. Which of the following graph shows the relationship between energy and frequency? Take a second, pause me, and pick your graph. All right, remember, as frequency goes up, so does energy. They are directly proportional. So graph number 4 is the only one that shows a directly proportional relationship that is linear. All right, I've got an example, you've got a problem, and then you're free. So we are going to calculate the wavelength of green light that has a frequency of 5.45 times 10 to the 14 hertz. So we've got light. So that means I'm going to use C equals lambda V. I'm sorry. Dang it. Let's just turn that into an F. I'm sorry. Not V. Lambda F. My bad. If it's light, what is C? 3.0, whoops, times 10 to the 8 meters per second. Frequency was given, we've got 5.45 times 10 to the 14 hertz. I know it's painful for you to watch me write out our givens, but it's super important that whenever you are solving a problem, you take the time to write out your givens. I can't tell you how many of you are making silly mistakes because you are flipping values around as you plug it into your calculator. Take the 20 seconds to write out your givens so that way you can see clearly what goes where into your equation. So now we've got 3.0 times 10 to the 8. We're just filling in our known information, equals lambda, the wavelength that we want, times 5.45 times 10 to the 14. If I want to get lambda by itself, I need to undo this multiplication that we see, which means we are going to divide, and whatever we do to one side, we got to do the other. So I'm dividing both sides by 5.4, 5 times 10 to the 14. Those will go away. Same thing over here. 4, 5 times 10 to the 14. All right, you will use your handy dandy calculadora. Take a second, try it, and see. I get that lambda equals 5.50 times 10 to the -7 meters. Now, this is fine. Typically with colored light though, remember I said we do nanometers. So to turn this into nanometers, the easiest thing we're gonna do, to go from meters to nanometers, you take your decimal and you move it 1, 2 to the right. Oops, oh no, 550, not 5.50. I moved my decimal. 550 times 10. I moved it 2 spaces, so I'm going to add 2 to this 7. So it's going to become a -9. Or, I'm sorry. Ignore me, guys. I'm an idiot. We just move it over 2 spaces, and we get that lambda equals 550 nanometers. There we go. If you want to just keep it in meters, that's totally fine. I might have just confused you because I'm an idiot, and I'm really sorry about that. But either of those options would be okay. And if you were to go back and look at our your electromagnetic spectrum, you should see that green light is somewhere in that 550 range. All right, we're going to move on before I say anything else stupid. I want you to try this. You've got to calculate the frequency of an electromagnetic wave that has a wavelength of 8 meters. 8 meters. Once you do your calculation, I want you to tell me what type of wave it most likely is. Please pause me, put up your answer, and then when you're ready, resume and I will walk you through the problem. So it's an electromagnetic wave. So we know that it's traveling at C, 3.0 times 10 to the 8 meters per second. 0 times 10 to the 8 meters per second. We've got our lambda, which is 8 meters, because it's giving me a wavelength, that's lambda. So we're going to set up our equation. C equals lambda F, okay? So 3.0 times 10 to the 8 equals 8 times F. If we want to get F by itself, we have to divide both sides. Divide by 8. Use your handy dandy calculadora. I got a frequency of 375 0 0 0 0 0. 1, 2, 3, 4, 5. Yep, that's it. Hertz, H-Z. You might have gotten on your calculator 3.75 times 10 to the 7 hertz. Both are totally acceptable. Either answer is fine. Good job. But we are not quite done. We also need to decide what type of wave this is. So when you're determining the type of wave, the easiest thing to do is look at the wavelength and see where would that fall. If you did not already do that, pause me again. Look at your electromagnetic spectrum that you copied down into your notes, because I told you to do that, and decide where would 8 meters fall as a wavelength. All right, you should have determined that this would be most likely be a radio wave. All right, radio. Radio. Excellent. Wasn't that fun, guys? I know, such a blast. Oh, and then here's this in case you forgot. I forgot that I put that there. So radio waves are between 1 meter and upwards of hundreds of meters, which is why this is a radio wave, but more specifically, it's an FM radio wave. Fun, right? All right, that's it. Hopefully that all made sense. Hopefully you took really good notes, because remember, we're gonna have a final exam soon. When you're ready, take the assessment and do great things. I love you guys a lot, and I miss you like crazy. Have a great day. Bye.